Okay, picking up from the last video, we built our histograms. Now what I want to do is some spike manipulations to show how the histogram changes as we change the probabilities of success. So this is the color blindness example. And our colorblind example was a success of 20%, which means a failure of 80%. So let's go back into our formula here and change the probability. Let's change it to 50%. And I want you to watch what happens to the histogram when I do this. Okay. Now I've got to pull this down, of course. Notice it becomes symmetrical. If instead I change the probability of success to, let's say, not 50%, but 80%, then it becomes skewed to the left. So what you'll notice is that as we go from a low probability of success, 20%, to a 50% probability of success, and ultimately to an 80% probability of success, we go from a left skewed to a right skewed distribution. Now we could do the same thing with our data on females. Here we have an initial distribution that had a probability of success of 40%. Okay. Well, let's change that to, let's go down to 20%. Go through the same process. Go to 20%, you'll notice that it becomes right skewed. You're getting lower values as the most likely to occur because the probability of success, in this case being female, is only 20%. It's low. But if I change this to, let's say, 50%, then it moves to be symmetrical, which means I have an equal probability of low numbers or high numbers. And then finally, if I change this to 80%, it becomes left skewed, which means very low likelihood of getting few females and high likelihood of getting a lot of females because the probability is 80%. So again, you see the same pattern as we did with the prior data. This slide shows us how to calculate the mean and the standard deviation of a binomial distribution. The mean, which is the expected value, is just your sample size times the probability of success. Whereas the standard deviation is going to be the square root of your expected value, NP, times the probability of a failure, which is 1 minus P. Another way to think about this is it's your sample size times probability of success times probability of failure, and then taken to the square root. Here's some examples. Let's say we have a n of 5, so a sample of 5, and the probability of success is 0.1. Well, 5 times 0.1 is 0.5. We would get an expected value of 0.5. And with that same data, we'd have a standard deviation equal to NP times 1 minus P, which would be 5 times 0.1, which we already said is 0.5, multiplied by 1 minus 0.1, which is 0.9, and you get 0.6708. So very easy to calculate the expected value and the standard deviation. And then down here, the only thing that's changing is our probability of success. It goes from 0.1 to 0.5, and notice that the standard deviation using the same formula goes up to 2.5. You can also see this in the graphs. So if you have a sample of 5 and a probability of success of 0.1, again, you're getting low numbers of successes. So the probability of getting a 0 success or 1 success is much higher than getting 4 or 5. But as you move from that 0.1 probability to 0.5, you move to a symmetrical distribution where the probability of getting 0 successes or 5 successes are the same. The probability of getting 1 success or 4 successes is the same. The probability of getting 2 successes or 3 successes is the same. So it kind of balances out on the high end and the low end. Another common discrete probability distribution is the Poisson. And this is similar to the binomial, but we use this when successes are defined across an interval of time or distance. So it's not successes versus failures. It's successes within the context of time or distance. For example, if we're looking at the number of potholes in a mile of road or emergency room patients per hour, you're either looking at time per hour or distance, miles, and you're measuring the number of successes. The other thing that has to be considered with Poisson is the number of successes in the time or distance interval must be identifiable. So you must be able to say there's 8 patients per hour or 10 potholes per mile. You have to be able to quantify that. That's a similar requirement to the binomial n must be determinable. Trials need to be independent with constant probability. Again, similar to the binomial, that you need independence and constant probability across your trials. So if we're looking at emergency room visits, we have to be able to assume that the probability is the same no matter what hour you analyze. If we're looking at potholes per mile, we need to assume the probability is the same no matter what miles you're looking at. The expected value of a Poisson distribution is NP, just like the binomial, and the standard deviation is similar. It's the square root of NP. Notice that in the binomial, it was the square root of NP times 1 minus P, which is the probability of a failure. But we can't measure failures in the Poisson, so we just get rid of that. It's essentially just the expected value rooted. All right, let's wrap up this section with an application. To do this, we're going to use Excel, and let me go ahead and pull up a new sheet here. It says a college switchboard gets an average of 3.5 prank calls per day. Using Excel, find the probabilities of 0, 1, and 2 such calls on a particular day. So the first step we do is just like we did with the binomial. We put our successes here. So 0 successes, 1 successes, or 2 successes. Okay? And then in the next column, we're going to put the correct function. Type in Poisson and pull that function up. Poisson.dist. Click on that one. And then your x value is going to be the information in the first column. Then the mean, it's given to you. It's 3.5. So we're just going to put in 3.5 here. And then again, we don't want cumulative for this one. So click on OK and change it to a %. And voila, there's your probabilities. Once you have that, you can then answer questions. Like, for example, what is the probability that they're going to get 0 crank calls? Well, 3%. What is the probability they're going to get 1 crank call? 11%. What's the probability they're going to get 2 crank calls? 18%. Easy enough. Let's go on to the next one. It says the probability that a soccer player will be seriously injured in a game is 0.003. There are 150 players in a particular league. Using Excel, calculate the probability that there are 0, 1, and 2 serious injuries during the games on a given weekend. Same process. In our first column, we put those discrete outcomes that could occur. We could have 0, 1, or 2 serious injuries. Okay? And then we put in the next column our formula, Poisson, and select the data. The mean, we don't have the mean here. We actually need to calculate it. Okay? And then to calculate it, what you do is just, let me actually get rid of that. To calculate it, you can just create a formula over here equals, we have n, which is 1 to 50, because there's 150 players in the league. Multiply that by 0.003, and you get 0.45. Okay? So that's going to be our mean. Now we can go back and use our formula and select the values, put the mean, which is 0.45, and not cumulative, percent. And there we go. So the probability of getting 0 serious injuries is 64%. Probability of getting 1 injury is 29%. The probability of getting 2 injuries is 6%. So very user-friendly. Excel is wonderful in this respect. But try to understand the meaning behind these and what you're really doing. I mean, you're dealing with a discrete probability distribution. So you've got these countable events, 0, 1, and 2, that you're trying to attach probabilities to. And you can use the Poisson if you can define success within a time or space interval. The last question here says, suppose that 30% of all students who apply for admission to U.S. graduate schools are accepted for admittance. 10 students attend a special seminar on how best to apply. Let the number of students who are admitted from this group be the random variable. So in this case, we can create another sheet here. Same process. We've got a success rate of 30%, and 10 students attend a special seminar on how best to apply. So it looks like our N is 10. We want to know the number of students who are admitted from this group. This one doesn't look like a Poisson because you're dealing with successes, 30%, but these also define failures. If 30% get in, then 70% don't. So this looks more like a binomial. In fact, I think one of the questions down here was identify the appropriate discrete probability distribution to use. Well, it's not the Poisson, it's the binomial. So we'll use that one. Okay. And we use the same process. So in our first column, we're going to put the possibilities. We could get 0 students that are admitted, 1 student, 2 students, all the way to, let's see here, 10 students, right? And then we go to the next column, find our binomial distribution, and click on number of successes. Trials, we've got 10 trials. Probability of success said it was 30%, and we're not going to use cumulative. Click on that, go to percent, pull it down. Easy enough. So let's see what the question is. It says, calculate the mean and standard deviation and construct a histogram. Well, here's where we can spot the mean pretty quickly. The mean is always the expected value, and isn't that the most likely to occur? So wouldn't the mean be 3? No, that one's pretty easy. Now you say, but don't we have a formula to calculate the mean? Yeah, the formula is NP. But what is N in our example? What's 10, right? And we multiply that by P. What is the probability? Well, it's 30%. So what is 10 times 30%? It's 3. So you can get the mean by using the formula NP, or you can just look at the most frequently occurring, which is 3, because that has a 27% probability. Now for the standard deviation, we would need to use the actual calculation. So at standard deviation, we know it's n, it's actually the square root of NP multiplied by the probability of a failure, which is 1 minus P, and that's all to the 25. Okay. So let's plug the numbers in. Well, what do we know? We have n, which is 10. We can multiply that by the probability of a success, which is 0.3. We can multiply that by the probability of a failure, 1 minus p, which is 0.7. And then we can take that to the, it's in brackets here, take that to the 0.5. And you get 1.44. Okay? Round that a little bit. 1.45. Okay, lastly, we can create our histogram here. To do this, we're just going to scroll over our data, right? Go up here to Insert, click on the columns. Again, get rid of the blue. Let's use a darker background. Double click. Histograms always have no gaps. So we got that. Again, we need to get rid of the 1 here and make that a 0. So we're going to go up here to select Data, Edit, and then pull this data here. Click OK. And voila, we have our histogram. So I think we've done everything that's been asked here. Alright guys, that's it for this video. I hope it helps. If you have questions, let me know.